Welcome back to Hands-On with Reinforcement Learning. We're now at a section where we talk about the multi-armed bandit environment. Now, if you have done any sort of Googling of reinforcement learning, because you're now immersed in this course, you will see this term a lot. In this video, we're going to follow on with our created MAB environments from the last video, and then talk about creating an agent to solve the multi-armed bandit problem. Because later on, we're going to leverage the power of neural networks and deep learning. I'm going to start trickling in some TensorFlow in this section already, so it introduces you how you can use an automatic differentiation package like TensorFlow to create the models that approximate the policy or best action or the values of different states that the agents and the environment is in. Specifically, in this video, we're going to look at how to create a class that contains a smarts agent to solve the multi-armed bandit problem. We're going to also talk about how to use TensorFlow to store the agent's policy in one of the TensorFlow variable. Now let's talk about how we can create an agent that optimizes a policy for the multi-armed bandit. The goal here is we want to apply a reinforcement learning paradigm to find the best arm to pull in a multi-armed bandit situation. Recall that in previous videos we talked about the hill climbing algorithm, where essentially you have an agent again that has a policy, and you move the policy and keep the new policy if this policy generates a better return, until you have a policy that generates the return you need, which is 200 steps of survival on the Kartspo environment. Creating an agent that solves multi-armed bandit is very, very similar. So if you go back to the multi-armed bandit.py, we have actually implemented this agent in an agent class, so to kind of encapsulate most of the logic. And because as this class goes along, we're going to use more and more complicated function approximators. So I've chose to include TensorFlow in this early agent so that we can get accustomed to how we use a library like TensorFlow to do calculations of policies in a reinforcement learning way. So if you come from supervised learning or general machine learning, this is actually going to look a bit weird, because in supervised learning, what you do is you have a data set, you feed that data set through your neural network or your model, compute the losses, and then you minimize the loss, and then you have a model that can do inference in the future. The way I think about models and neural networks in reinforcement learning is more that you use the variables, you still update the variables, and you still, or parameters of your network, and you still pass it multiple different data points. But the difference is because the data points now needs to be collected in episodes and as you run through the environment, such that you actually have a much more complicated training loop. And therefore, at least the way I think about it, is that your network parameters almost serve like a memory or like a state variable within your agents class, that a set of variables where you store the current best estimate of the policy that would make you a winning agent within that environment. So this sounds very abstract, and I really hope that by implementing this yourself, it will help you understand how to use machine learning in a reinforcement learning problem. Let's jump right into it. So agents is structured into 4 different functions. In the function that initializes the class, we build the set of variables that hold the approximator to the best policy. We also, as per general TensorFlow convention, build up a loss function so that we can continually train the policy according to what our actions rewarded us. There's a predict function, which is simply a wrapper onto the computation graph that allows us to extract the best action to do given the current policy. There's another function, random or predict. Now this is quite interesting. So recall that earlier in this section we talked about the exploration and exploitation trade-off. So one of the very simple ways to approach this trade-off is we have an epsilon function. To deal with exploration versus exploitation, a simple scheme is to have a parameter, usually epsilon, to control whether the agent explores or exploits. So random or predict is a function that allows us to do that. The last function in the agents class is the train function. So the train function simply accepts an action, the resultant reward of the action, and then moves the policy to reflect the fact that the particular action resulted in a particular reward. So let's see how we implement these functions. The first thing to do is to create the computational graph that represents the model of the policy for the agent. So we will keep track of the number of actions. We'll create a new value with a TF placeholder for the reward to come in. We'll create a similar thing for the action. And as I said before, this is actually it's not even a model, it's basically 4 numbers to keep track of what the payoffs between 4 different arms. So here we simply say we'll get a weights matrix that has 4 slots in it. And the best action is to pick the largest number in this weight matrix. And then what we need to do is to create a mechanism so that we can feed back the action we picked, the reward that the action resulted in, and get the agents to actually calibrate the model of the policy so that the model can then maximize the reward. So what we do here is when we feed in the action, we actually use the slice function to find the responsible weight. After we've found the responsible weight, put in action weight, the loss is simply the action weight times the reward. So if the reward that was fed in is positive, then we encourage that action to be higher. If the reward is negative, then we encourage the action weight to be lower. Very easy. And then very standardly, we create an optimizer for this loss with the standard parameters. So now that we have this training graph, what we then need to do is to wrap different tensors of the training graph in different functions so that it's slightly more clean. So only the agents class touches its own model and nobody else touches the model. So in a predict function, we simply say you're supposed to run the best action, very easy. And in a random predict function, as I said before, the idea here is to approach the exploration versus exploitation trade-off with an epsilon parameter. And if the epsilon is, so we can generate a random number, if that's smaller than epsilon, then we basically pull a random arm so that we start collecting data from an arm that isn't necessarily the best arm for us to pick. Otherwise, we will use our model to predict what's the best arm to pull, and then continually pulling that, so to maximize the reward. So, very quick recap. If we generate a random number that is smaller than epsilon, then we do exploration. If otherwise, we do exploitation to maximize the reward. The very last thing we need to do is to create a function that could run our optimizer and feed in the action we did and the reward it resulted in. So very easy, feed in the session, we run the optimizer, and because we have created placeholders for the reward and the action to come in, we can then just feed it in from the training function. Great. Now the agent is done, and we need to train the agent and understand what it has learned, and also figure out whether it has learned the right thing. For that, we'll go to the next video. See you next time.